Ready, Hedrick? Here we go. I wrote down here, video, how fast does time slow down? I actually showed you that one a couple of days ago. That was where Brian Greene had the two clocks, and you noticed it was really tough to see any difference until you got near light speeds. Then you could see the difference. So here's the question we want to ask a little bit. Why don't we notice special relativity in our everyday lives? Well, look at the time dilation equation, which is time standing still equals the time of the moving object divided by the square root of 1 minus v over c all squared, or v squared over c squared. And then what I want you to do is I want you to circle that. We call this circled section the square root of 1 minus v squared over c squared, the Lorentz factor, named after a scientist whose last name was Lorentz. Okay. He was slightly before Einstein, but he also believed that the speed of light was constant, and he actually, to explain it, tried to suggest that somehow atoms were changing size or something weird was going on. He tried to offer an explanation, but he was actually a mathematician, and so he said, look, I can tell you when I crunch the numbers, that factor there seems to be what makes it work. So we call this circled section the Lorentz factor. It's often symbolized with the Greek letter gamma. Greek letter gamma looks like that. It sort of looks like a fish standing on its head. And so you may, in a textbook, see that. This is what determines how much time dilates. This is the time dilation factor. And so you may see Einstein's equation written this way. Which is less writing. So what we're going to do is we're going to, on our calculators, try typing in that 1 minus v over c all squared square root. And just kind of see what happens. Here's our question. How much will 1 hour of time dilate for the following situations? And I picked 1 hour on purpose because that means t0 is 1, and so I can ignore the top. Okay? So, if you're walking, your speed is 2 meters per second. What I would do is I would put a 2 right there. So if you want to get out your calculators, working? Yeah, there we go. And on my calculator, I'm going to type 2 divided by, and the speed of light is 3 times 10 to the 8th. There's my v over c. You're going to get probably a really small answer in scientific notation. Squared. 1 minus that. Square root, and do you notice what happened on my calculator, which is probably better than any of your calculators? It's so small, my calculator couldn't keep track of the decimals. All of a sudden, I ended up getting as an answer a 1. It was really 1.000, some really small decimal, probably 1.00, probably 40 zeros and then a 1, but my calculator couldn't handle it. And so it turns out the Lorentz factor, the time dilation factor when you're walking, is so close to 1 that we don't notice it. Hey, Courtney, maybe a race car might notice time slowing down. In a race car, you're going about 70 meters per second. Okay, so I'm going to go 70 divided by the speed of light. Squared. 1 minus that. Uh-oh. You know what? I'm going to quit right here. As soon as my calculator stops carrying the decimals, I know, Hedrick, it's so small that my calculator can't track it. You know what? The time dilation factor for a race car, it's basically 1 to 1. Technically, Alicia, it isn't, because you could see I did have decimals on my previous line. Yes, see them there? But when I went 1 minus that, my calculator said, are you kidding me? And I haven't even done the square root, which would make it smaller yet. Ooh, what about an SR-71 jet fighter? The fastest jet fighter ever made. That travels at 1,000 meters per second. Let's try that. So I'm going to go 1,000 divided by 3 times 10 to the 8th. Here's hoping, Ryan. Maybe the jet fighters, maybe for them it's noticeable that time is slowing down. Squared. 1 minus that. Technically, I should now go square root. Did my decimals vanish here again, Ryan? So you know what? Even traveling that fast, now we have been able to measure it with very accurate atomic clocks. I showed you the video, but that tells you how accurate those clocks must have been, because my calculator can't calculate it. I think those clocks were accurate to something like 50 decimal places. Oh, okay, then it was noticeable. But it was. We have measured it experimentally. What else can you think of that goes faster than a jet? Oh, how about the Earth around the sun? That goes pretty fast. Okay. So now, again, what we're calculating is 1 over, oh, sorry, wrong symbol. The Lorentz factor, the time dilation factor. We're calculating 1 divided by, you guys haven't turned the page, have you? I have. 1 minus V over C all squared. So let's see what this gives me. 29,600 divided by the speed of light squared. 1 minus that. Decimal hasn't vanished yet. Square root. 1 divided by that. Woohoo! The fact that the Earth is moving around the sun at 29,600 meters per second says that if somebody, well, the sun, which is standing still in the center, it's experiencing time slightly faster than us. Our time is slowed down, and our time dilation factor is how many zeros? 1, 2, 3, 4, 5, 6, 7, 8. 8, okay. 1.8 zeros. But the sun is aging slightly faster than us. Yay! Oh, wait a minute. We kind of don't want the sun to age faster than us, because when the sun burns out, we're out of luck. Hey, you know what? I looked this up. The Earth and the sun are also moving through the galaxy. How fast? About 2.1 times 10 to the 5th. So the center of our galaxy is standing still relative to us. There is going to be a time dilation between the center of our galaxy and us. How much? Divide by the speed of light squared. 1 minus that. Square root of that. And then 1 year divided by that time dilation factor, and whoop. What did I have? 1, 2, 3, 4, 5, 6 zeros and a 2, 4, 5. 1, 2, 3, 4, 5, 6 zeros and a 2, 4, 5. Cohen, my point being, even at that speed, which is 21,000 meters per second, 21 kilometers a second, even at that speed, you wouldn't notice the time dilation factor, because that's such a small number, you wouldn't be able to detect it. Well, UBC has a cyclotron, a particle accelerator, and there they get the protons going pretty fast. They get the protons going at 2.24 times 10 to the 8th meters per second. What does time slow down for those protons? Well, so now the protons are like a spaceship traveling, so that's V divided by the speed of light squared. 1 minus that square root. 1 divided by that. In 1 year, The protons will experience, hey, that makes a difference. 1.5 years. That's noticeable. What's the speed of light as a number? 3 times 10 to the 8th. That's why I've been putting in that 3 times 10 to the 8th in the bottom. So this was 2.24 times 10 to the 8th. Turns out at the Large Hadron Collider at CERN, we can get muons going at 2.996 times 10 to the 8th. Very close to the speed of light. So in 1 year for us, because now we're standing still relative to the muons, how much time, in 1 year for the muons, how much time would go by for us? Okay, 2.996 divided by 3 times 10 to the 8th squared. 1 minus that square root. 1 year divided by that, so 1 year on the muons would be, 19.4 years for us. Okay, that's making a difference. By the way, Prith, 2.996 times 10 to the 8th divided by 3 times 10 to the 8th times 100. We're getting to 99.87% of the speed of light. That goes to your question from number 18. Turns out we can get electrons to go faster at the Stanford Linear Accelerator, or the SLAC facility as it's nicknamed. We can get those going to 2.9979 times 10 to the 8th. So 1 year of an electron's life, how many years would that be on the Earth? Squared. 1 minus that square root. 1 divided by that. 26.7 years. Is that okay, Court? Really, the reason I walked through this is not just because to me it's nerdily interesting, but I wanted you to realize, not as a shortcut, but as getting quick, it's really the most complicated part about time dilation is the gamma factor. And so hopefully you got good at typing. You've already, last day we mostly did the percentage of the speed of light, and so the C canceled. Here we did a bunch of examples where I actually gave you the speed, so you had to include the speed of light by dividing by 3 times 10 to the 8th. Hey, would you like to see time dilation illustrated within 10 seconds? Have I got a video for you? It gets weirder. Do you remember last day we did the traveling to Proxima Centauri question? And we noticed that even though the Earth thinks that that star was, I think it was 4.24 light years away, a fast-moving ship would measure a completely different length. So, Einstein's special theory of relativity makes other predictions about objects moving at speeds greater than 0 without going into the mathematical detail. We'll simply state that it predicts that lengths get smaller in the same direction that you're traveling. Turns out we can describe that with an equation. Turn the page. Now, the only problem here is the 0 and the L are the opposite of time. In time, T0 was the moving object, and T was the Earth back home. In the length equation, L0 is what's standing still, and L is what you see when it goes whizzing past you. Turns out the length of a moving object is equal to L0 times the square root of 1 minus v squared over c squared, or Cohen, as it's sometimes written, L equals L0 gamma. That's why I snuck that in earlier. Did I put that on your formula sheet? I did, because one of these we're going to do an equation that I forgot to put on, but this one I did. Now, here's the problem. L and L0 mean the opposite of what they did in the time equation. T0 was on the spaceship moving. T was back home. Here, L0 is, 0 original length. I think LO original. And L the moving length. If you're looking for a dumb way to remember it, that's what I'm going to go with. So L is the and L0 is the original length at rest. By the way, if you're at rest, what's your speed? 0. I use all of this to remember that L0 is the length at speed 0. LO is the O original length. Whatever works for you. So, how long would a meter stick appear to be if it moved past you with a speed of 0.995 times the speed of light? 99.5% of the speed of light. Now, if you were sitting on the meter stick moving at the same speed, as far as you were concerned, the meter stick would still be a meter. But if you saw it whizzing past, and if you could see things that fast, well, this is asking us to find that. I hope this is obvious. What's the original length of a meter stick? Okay, 1 meter. And the speed is 0.995 times c. So we have this. L equals L0 square root of 1 minus v over c all squared. One square root of 1 minus 0.995 c over c all squared. Rebecca, this time am I going to need to type in the 3 times 10 to the 8th in the bottom, or is there c on the top and the c and the c's cancel? Oh, that's kind of cool. In fact, you know what? I think it's just going to be inside the square root 1 minus 0.995 squared. Square root. And then it's times 1. Will multiplying that by 1 change the answer at all? So you know what? A meter stick would look to you like it was, well, 9.998 centimeters. You know what? 0.1. This rounds off to, right? It'd be 10 times shorter. It'd be 10 times shorter. To you, you would swear that that meter stick was this long. And you would see all the numbers smooshed in correspondingly. Now, but here's the weird part. You wouldn't notice that the width had changed because the width is not in the direction of travel. You would see this short, stubby little thing. An 85-meter long spaceship passes you at 2.23 times 10 to the 8th meters per second. How long does the spaceship look to you at rest? What's this question asking me to find? L or L0? L. Okay. So they must have told me the original length. 85. And V is, they didn't give it to me as a percentage. So this time, Rebecca, I am going to have to type the 3 times 10 to the 8th in the bottom. Okay, I just got pretty good at that with some practice. L equals, do I have the equation on the previous line sitting right there? I'm gonna go straight to plug and chug. 85 square root of 1 minus 2.23 times 10 to the 8th all over 3 times 10 to the 8th all squared. 2.23 times 10 to the 8th divided by 3 times 10 to the 8th squared. 1 minus that, square root of that, times 85. Again, I really encourage you to practice these on your calculator because it's some heavy-duty calculator work, especially if your calculator is, what's the word I'm looking for? Lacking. I got 56.86. I'll go 56.9. Yes? No? Yes? Anybody else? Yeah. 56.9 meters. And again, the widths would not have changed. So you can kind of use your imagination. You know what? It's like if you've ever dragged a box, a frame box, or a photo on your computer and you made it narrower, but it didn't change the height part of it. That's what we're talking about here. But here's the weird part. The people on the ship don't notice this at all. Everything would look normal for them. Suppose a spaceship is 100 meters long when stationary. When it moves past the observer measures the spaceship to be 25 meters long. How fast is the spaceship moving relative to the observer? Whew. What's this question asking me to find? Okay. Okay. So that must mean they gave me L0 and L. What's L0? What's L? You know what? Let's derive a new equation for V. And if it's ugly, we'll add this to our formula sheet too. And you'll know to use this one to find V because it's got L's in it. You'll know you'll use this one to find V if I give you lengths, as opposed to the other one you wrote, which is finding V if I give you, what did the T's stand for? Time. Okay. So my equation looks like this. L equals L0 square root of 1 minus V over C all squared. Did I leave lots of room? Oh, good. Okay. Matt, see the V? What side is it on, left side or right side? And it's inside the square root, and I'm going to do reverse BEDMAT, so I'm going to deal with the square root later and that bracket later. I'm going to deal with this guy first. What's this L0 doing to the square root? Adding, subtracting, multiplying, or dividing? How will I move it over? So my next thing I would say is, I guess L over L0 equals the square root of 1 minus V over C all squared. What is that V sitting inside of? A great big what? Even bigger, a great big square root. How do I get rid of a square root? Huh? You did it yesterday. What's the opposite of square rooting? We're going to square both sides. So now I'm going to go like this. Square that, square that, square that, which really is just going to get rid of all that. The square and the square root will cancel. I'll end up with L squared over L0 squared equals 1 minus V over C all squared. Matt, I'm coming back to you. See the V over C in brackets? What's right in front of that bracket? I don't like that. You know what? I'm going to plus this there. At the same time, I'm going to minus this there. I'm going to get V over C all squared equals 1 takeaway L squared over L0 squared. Psst. Look up, look up, look up, look up. Really, That's the same as squaring both. Yes? So if you want to, you can scribble out the bracket and put a squared on everything. Matt, what am I trying to get by itself? What else is on the same side of the v? A c squared. What's a c squared doing? Adding, subtracting, multiplying? Huh? How do I move it over? Okay, so my next line, the v squared is going to drop down like a domino. The 1 minus L squared over L0 squared is going to drop down like a domino. But I think you told me I'd end up multiplying that by a c squared? Sure. I'll put it in the front because that's how you're used to seeing FOIL in math, right? The smaller thing in the front and then the bracket. I'm almost done. I've got the v squared by itself. Oh, we've seen this dance before. Help me out. How do I get rid of a squared? Okay, so here's what's going to happen. I'm going to go like this. Square root, which will cancel that. I'm going to square root this. I'm going to square root this whole big thing. The v is going to drop down like a domino. Yay! What's the square root of c squared? Just plain old. Yay. And inside the square root, we have 1 minus L0 squared over, sorry, not L0 on top, my bad. L squared over L0 squared. You might want to throw that somewhere on your formula sheet, maybe in the relativity section. And now, let's plug and chug. It's going to be ugly plug and chug, but it's going to be plug and chug. How fast? The speed of light, which is 3 times 10 to the 8th, times the square root of 1 minus 25 squared over 100 squared. Okay. I got sneaky. I decided to see if I could try typing that in one fell swoop. You might be able to. If not, you can still do the 25 squared divided by 100 squared equals 1 minus that equals square root equals times 3 times 10 to the 8th. But this one, because I'm not dividing by a bunch of stuff, you might be able to type that. I think you're going to get that. See if you doing it in chunks or all in one fell swoop. Is that okay, Matt? Yep, okay. 2.9 times 10 to the 1, 2, 3, 4, 5, 6, 7. Oh, 2.9 times 10 to the 8th, just below the speed of light. Get that okay, Hedrick? Good. Meters per second. Or, Prith, if I wanted to change it to a percentage, divide by 3 times 10 to the 8th, and then times 100. 96.82% of the speed of light. So there's still room to go faster. Here's the star question, the Proxima Centauri question, except now because we have an equation for length, for distance, we can maybe get there a little more cleverly. It says this: a certain star is 15.6 light years away. How long would it take a spaceship traveling at 0.95 c to reach the star? Well, first of all, as measured by stationary observers on the Earth. Can you underline the word stationary? Because we're talking about the Earth and relative to the Earth and stationary, we don't need to use Einstein. We can simply say time is the distance divided by the speed. The distance is 15.6 light years. Can you all look up for 1 second? Just watch. The speed is 0.995. Now, I wrote c, but what does c stand for? Speed of light. Really, you can think about it as 0.95 times light. And what I want you to realize, Connor, is you're going to get an answer in years. It's really 15.6 divided by the percentage, and that tells you how long in years the lights cancel. That's not quite good unit analysis, but that is an okay way to think about it. Okay? As far as we're concerned, it'll take them 16.42 years. I'll carry a few extra sig figs. B. As measured by observers on the spaceship. Okay, that's going to be T0. How do I get T0 by itself? Was that this one? Was it yeah? Yeah, T, okay. To find T, you divide by the T0 by the gamma factor. To find T0, you multiply T by the gamma factor, by the Lorentz factor. Was that right? Yeah, I'm going from memory, but I'm pretty sure that's good. 16.42. I'll use my answer button. Square root of 1 minus, hey, they gave me light as the speed as a percentage, 0.95 c over c all squared. Rebecca, is there a c on top of the little fraction? Is there a c on the bottom of the little fraction? So really, I'm just going to go 1 minus 0.95 squared. 1 minus 0.95 squared. You know what? I think I can do this one in one fell swoop. Now, maybe I'm good enough. 16.42 square root bracket 1 minus 0.95 squared close bracket. That gets me there on mine. And this is where it's going to vary on how good or not your calculators are. Trev, I got that? Yes? So, oh, you didn't do it. Okay, 16.42 years for us on Earth. Actually, for the space travelers, they're only going to notice 5.127. Really, I should have used my answer button. I typed 16.42. If you use the answer button, you might notice a slightly different answer. I don't know. I'm going to go 5.13 years. C. For part C, I'd like you to draw a little line down the middle of your page. Yesterday, we found the distance by going like this. Distance equals speed times time. Which time? The time on the spaceship. And so we found the distance by going 0.9, whoop, not 99, 0.95 c times 5.13 years. But then I said if you ignore the c, that'll give you an answer in light years. And we said as far as the ship is concerned, they're going to find that it's 4.87 light years away, as opposed to 15.6 light years away. They're going to measure, for them, the distance has contracted. I'm going to say the same thing, but I'm going to phrase it differently. The length of their trip has contracted. You know what? Maybe we can also find this by going I don't think I put a bracket there, did I? Let's try that again. Square root of 1 minus v over c all squared. What's the original actual length? How many light years do we measure at rest on Earth? I've scrolled down. What was it? 15.6? Square root of 1 minus 0.95 c over c. Rebecca, is there a c on the top? Is there a, yay! So if I go 15.6 square root of 1 minus 0.95 squared, there. Do you remember, I'm just going to hit pause for a second, you guys just stay there. I said to you, without going into mathematical detail, there's the mathematical detail. We proved it 2 different ways and got the same answer 2 different ways. It's a natural consequence of the time dilation. So I don't care which method you use, Courtney, to find how long the trip is relative to the ship. If I just asked you part C and I didn't walk you through part A and B, I would go straight to the length contraction equation. I would. Yeah. Oh, light year. Thank you. Thank you. Distance. Yes. I made the Han Solo error. You know what the Han Solo error is? In the original Star Wars, he said the Millennium Falcon is the first one to make the Corellian run in 12 parsecs. Parsecs is a measure of distance. Every ship does the Corellian run in 12 parsecs because apparently the Corellian run is 12 parsecs long, but they've treated it as a unit of time, and they even brought it back in the new Star Wars. I was screaming at the screen. Although, says Prith, Mr. Dewick, maybe what Han Solo was saying is the Millennium Falcon is so fast that it can travel so fast that it contracts the length so that for it the distance is only 12 parsecs, but other ships it's a longer distance because they can't travel as fast. That's what George Lucas has tried to claim, but initially he admitted he just screwed up on his units. Hey, what does this mean for an object that travels at the speed of light, like a photon? Okay. Courtney, how fast does a photon travel? At the speed of light. So a photon would put a C right here. So are you still writing down? Okay. Look up and just watch for a second. A photon would put a C right there. In fact, you'd have C squared over C squared. Courtney, what's 5 divided by 5? What's 10 divided by 10? What's C squared divided by C squared? So this would work out for a photon to 1. And then you'd have 1 take away 1. Courtney, in your head, what's 1 take away 1? 0. What's the square root of 0? What's anything times 0? This is another proof that for a photon, everywhere in space is no distance away. As far as a photon is concerned, it's everywhere in the universe because there are no distances for it. Pretty cool. I'm going to pause here. However, right now, by the way, you're going to find out it gets even stranger. This one I'm not going to prove mathematically, but we're going to find that as you speed up through some mystical process, your mass increases. Things get heavier. And this is the one that I forgot to put on your formula sheet, but we'll do this on Tuesday. For now, you're capable of, from this homework, of doing number 1, of doing number 2, doing number 3. 4 is the length question. 5 is the length question. 6 is the length question. 7 is a length question. And 8 is a length question. 9 and those are all mass. We'll do those next class. So your homework right now is going to be finish the quiz, lesson 2, and then you can start lesson 3. But I got to short